We're going to talk about fuzzing here today. A large part of today is going to be focused on just fuzzing some applications and finding and really generating a bunch of crashes. That's what fuzzing will do. We'll end up with like this large body of crashes, and then we're going to analyze those crashes for whether or not we think they're exploitable, whether or not they represent an underlying exploitable vulnerability. So like I mentioned before, in exploits 1, fuzzing is basically the process of feeding in an application malformed data. All right, and you do this at like a very fast rate, and it's nice because you can program a computer to do this. It's not something you have to waste your own brain cycles on. So that's the real advantage of fuzzing, is that you can just program a computer to do it, right? It's hard to program a computer to reverse engineer, but you can program a computer to just keep hammering an application with malformed data. And this became really in vogue like around 2007 or so, and they sort of predicted that it was going to die off and like not be useful. After a while, that it would just kind of find all the bugs it was going to find, and then they would disappear. But they also predicted the death of the bug overflow by like 2005 or something, and it's definitely still around. So fuzzing is still effective for finding vulnerabilities, definitely. And it's very well suited for trying to find the type of client-side vulnerabilities that we're looking at, where you're like rendering a document or doing some sort of parsing or something like that, like a web browser vulnerability or a PDF vulnerability. It's very well suited for that type of vulnerability discovery. Okay, so fuzzing definitely isn't the end-all, be-all. It's just one strategy that you can apply for trying to find vulnerabilities. Like I mentioned before, the pro is you can program a computer to do it. You can make it a parallel process. You can just, increase the rate at which you're finding bugs by using more and more computing power. And computing power is a lot cheaper than people power, right? The other pro is it still works. It's good. The con is kind of the flip side of this coin. If anyone can program a computer to do it, then anyone else can find your bug, basically. And the best quality bugs are the ones that are going to be difficult to find, long-lived, not easily reproduced, something that you find by a deep understanding of the program, and if you didn't tell the vendor, it would probably last for like 10 years before someone stumbled across it. But if you just found it with fuzzing, there's a good chance someone else is going to come along and fuzz that application and find the same bug. So it's, maybe not as good because it won't last as long before it gets out there in the public knowledge. So my analogy for fuzzing is it's like, trawl fishing in the ocean. You just have this big net and you're just looking for whatever you can find. So the real crux of fuzzing is the malformed data, how you go about generating this malformed data. And there's kind of two ideological approaches you can take to this. The two approaches are mutational fuzzing and generational fuzzing. So with mutational fuzzing, you take an existing body of like known good data samples and you change them a little bit before you feed it to the application. You like flip some bits, which is basically what we're going to do before you send them to the application. And that's good because we can just go out and download a large body of known good data samples. So if we were fuzzing PDFs, we could just write a script to go and download every PDF we could find on the internet. And the alternative is generational fuzzing, where we basically understand what the data is supposed to look like. So, for instance, we know all the specifications for what the PDF document is supposed to look like, and we sort of describe that in like an XML format. And then we have a program come along and automatically generate documents based on the specification, and then the generator is sort of smart to trying to generate cases that are on the limits of what's an acceptable document according to the specification. So generational fuzzing is good because it generally produces better bugs. When you really understand the document format that you're trying to fuzz, you can really try to hit all the corner cases precisely. The con here is that you have to, understand the complete specification of what you're fuzzing, and that is often difficult or not tractable. So most of the time we're fuzzing like proprietary application, and the specification might not be known. So you would have to spend a lot of time reverse engineering what the specification is supposed to be, and that's very time consuming. If it's an open specification, this becomes a lot more tractable because you can just look up what the document is supposed to look like, but a lot of times it's proprietary and you have to reverse out exactly what the document is supposed to conform to. But in general, this approach yields better bugs than mutational fuzzing. Okay, so mutational fuzzing is the big advantage here is it's very easy to do. Like I said, you can just go and download a script or write a script to download a whole bunch of PDF documents or whatever document it is you're trying to fuzz. It's not quite as good in general. Empirical evidence shows doesn't generate quite as good of bugs as mutational or as generational fuzzing, but it still works and it still generates bugs. So why not? Why make life harder on yourself if this approach is going to work? Okay. So for our purposes, we're going to be using a mutational approach because it's easier, because like I said, this class isn't about reverse engineering. I don't want you guys to have to use IDA-Pro for 6 hours to figure out what Corey's crappy document specification is. Instead, I'll be providing you with a sample of known good CDF files, and we'll be fuzzing those. And what our data mutation is, and this will actually be up to you someone, I'm going to give you some flexibility to change this, is we'll be changing a random byte in the CDF file to a random value. So one byte in the file changed to one random value. And I'll give you the opportunity to change those rules, and you can mutate the data based on however you want to, but that'll be our basic framework at least. So I was concerned when I was making this that people wouldn't really believe me that this works, but it definitely does. There was a talk a few years ago, I think it was Charlie Miller, made the talk about, what was it called? Like buzzing some products, like an army of monkeys or something like that, he called it, with basically doing the same thing that I just described. And he found all kinds of juicy vulnerabilities in these types of products by fuzzing their documents. And even today, this method still works. For instance, while I was making material to this class, just to get a data point, I put the XPDF reader in my sort of fuzzing framework, which is like a Linux open source PDF reader, and fuzzed PDF documents over like a weekend, and I got like 3,000 crashes over a weekend in XPDF reader, and a lot of them look pretty interesting. So there's definitely found some vulnerabilities there. I didn't really want to go into developing exploits for them because the company wouldn't like that too much. But I just want to justify that what I'm telling you actually works in the real world. And if you go and take this approach after the class is over, I guarantee you will find bugs in these type of client-side document parsing applications. Okay, so there's lots of other methods you can use for trying to find bugs. Fuzzing is just one particular tool in your toolbox. The fly fishing approach, as opposed to trawl fishing, is reverse engineering, which is basically where you're putting an application that you want to hack into IDA-Pro and very carefully understanding how it works and figuring out where some vulnerabilities may lie. So for those of you that use IDA-Pro, I'll just talk about this for a few minutes. I don't want to go into too much detail because this class is not about reverse engineering, and knowing IDA-Pro is not a requirement. So whenever I'm putting a program into or want to find bugs in it, the first thing I'll do is I'll put it into IDA-Pro, and I'll go to the import section and see what type of functions it's importing. And if I see it's importing functions like sprintf, string copy, scanf, all these sort of unsafe C functions, I know, okay, this program probably has a bug in it because it's using all these unsafe functions. And then what you can do is, like, okay, well, I know it's using WSPrintf, which is potentially vulnerable since it's like an unbounded data copy. So what I'll do is I'll go to the import sections where sprintf is and do a cross-reference on it. IDAPRO allows you to figure out where all that function is called. Okay? And so then I can see, all right, well, sprintf is called in these blocks of code in this application, and I just sort of jot these down. Like if I can get EIP in this range into this function, I'm probably in a function that has a vulnerability. So my general approach is, I'll go and identify these blocks that I think may be vulnerable because they use these vulnerable functions, and I'll just sort of mark them both with colors just to make it easier to see in the mini-map screen. And also I'll make bookmarks on there. And then what I'll do is I'll set a breakpoint on where the attacker data enters into the file and enters into the process, like on a read call or a read socket call or something like that. And I'll just start instrumenting the execution of the program to try to reach one of these red blocks. And I know if I can make the program reach one of these red blocks, then I could probably hit a vulnerability. The only question here is if by the time I get to this function, is it attacker-controlled data? So that's often hard to answer. A lot of times you can tell or have a good intuition about whether or not you think it will be attacker-controlled data when you get there by, like, for instance, looking at sprintf, it's going to also push a string onto the stack that represents, like, format string. And if I see that it's like, username modulo s just tried to log in, and I know that I control what the username is, that's good. But if it says something like configuration file contains a error in it, then I'm like, okay, well, as an attacker, I probably don't control that configuration file or something like that. So even though it's using a vulnerable function here, I don't control the data, so it doesn't really matter to me. Is there anything more I want to say about that? So part of the hard part with this approach, though, is you figure out where the attacker data enters into the process, like the read call or read socket call, and you know where the potentially vulnerable blocks are, and you want to try to get from point A to point B. So it sounds easy in theory, but it can actually be very difficult, especially with C++, and you have crazy things like calls through registers and stuff that's hard to, you can't just get from point A to point B with static analysis. There are some really good tools like IDAPython, which allow you to sort of script this path-finding functionality, where you can say, all right, I'm at location A in the program. I know this because I've been like stepping through the program with attacker-controlled data. Can I get to this block? And you can program IDAPython to do like a depth-first search and try to go out and see, all right, there is a path to this block, and this is how you would get there. And so based on that path, you can try to derive how you should manipulate the data so that the program will take that control flow path and get to that vulnerable block. So somewhat easy in theory, but it can turn out to be pretty difficult when A and B are very far apart. And you get there with crazy things like polymorphic calls and calls through registers and that kind of thing. Another approach you can do for finding bugs that I do, some more of my secret sauce, is figure out wherever memory allocations are happening by looking at calls to alloc or malloc or new or whatever, and do a cross-reference on those and see if there's like arithmetic or multiplication happening before them. And if there is, there's a good chance you can cause an integer overflow. Because like I mentioned in exploits 1, whenever you're doing arithmetic or multiplication on attacker-controlled integers, the attacker can make those integers, arbitrarily big and cause the multiplication to overflow and round back down to a lower value, and then it's possible you generate an overflow that way. So just a couple good tricks for you guys to know there, for those of you that are familiar with IDAPRO. Okay, so we're not going to use this approach though, and I'm not really going to talk about it more because reverse engineering is out of scope for the class. If you're interested in this approach, we do offer a course on reverse engineering. I believe Matt Briggs teaches it, so that'd probably be a good one for you to take. And in the future, I might try to offer a class where I'm focusing more on using reverse engineering to find bugs. Generally, when I'm looking at trying to find bugs in like remotely exploitable situations, I'll first go to reverse engineering, because it can often be a little bit wonky to set up fuzzing with these sort of like proprietary network protocols. But if I'm fuzzing something that's like a client-side parsing or client-side rendering application, then fuzzing is pretty easy to do, because I can just go and download a large sample of known bit files and start flipping bits. But ultimately, I pretty much always end up using both methods, because you can program your computer to fuzz and be using your CPU cycles to fuzz, and simultaneously be using your brain cycles to reverse engineer the application. So looking for bugs in two different methods in parallel. And basically what will happen is I'll write my own fuzzer, and I'll be reverse engineering, and then ultimately, while I'm reverse engineering, I figured out some more things about the document specification, and that allows me to make my fuzzer a little bit better by incorporating that new knowledge into my fuzzing framework. Okay. Let me just sort of justify that a little bit on the board. So could I come over here to the board, Bill? Okay, so the key part of fuzzing is what is known as code coverage, which means you want to exercise all possible code paths in the program that you're trying to target. So again, I'm going to draw one of these like IDA-Pro block diagrams that represents the program and its possible control flow. And obviously in real life it would be extensively more complicated, but for our purposes I'll just make it relatively simple. All right, so like an IDA-Pro, we have these blocks that represent like blocks of code we can get to. And a lot of time what you'll do when you first start out fuzzing, you'll just be fuzzing this control flow path. You'll just keep going on this code, and only this code will be exercised. And that's not advantageous, because if there are vulnerabilities in these blocks of code, then you'll never discover them, because you won't be exercising them. For instance, we could say that it only takes this path right here if offset forward to the file equals the string shockwave. If there's some string in there that indicates that the document has extra functionality. And so if we were just generating this data randomly, or we weren't using a sample size that had this shockwave string, we would never exercise this code path, and if there are any bugs down here, we would never find them. So the key with fuzzing is we want to have our fuzzer and have our data set exercise all of these possible code paths. So the way we do that is either through reverse engineering the specification and knowing that to hit all these possible code paths, I need offset forward to equal shockwave, to equal mime, to equal MP3, and all this other stuff. Or if we're not doing generational fuzzing, we basically need a large enough sample size so that all features of the application are exercised. So if I'm fuzzing like PDF reader, and PDF reader can do things like play MP3s and embed Flash videos and embed Excel documents. I don't know, I'm making this stuff up. I don't know that much about PDF. Then we would want to include PDFs in our sample, in our fuzzing sample set that used all of those features. That way we can exercise all of these possible code paths in the PDF program. Does that make sense? One bad thing about just sort of like random fuzzing as well is there are some bugs that you'll just sort of miss through this sort of like random data generation fuzzing that you would easily spot with reverse engineering. So for instance, if there's some line in the program that says like, if x equals ox, 1, 3, a, f, some magic tag value that's supposed to indicate something. Then do a string copy buff, attacker data, buffer overflow. If we are fuzzing, just sort of randomly generating data and didn't really understand the document specification that well, the chances of us generating this case, if x equals this, are astronomical, and we probably never would, so we would never find this bug. But if we were reverse engineering, we would see this line and spot the code and say, oh, okay, well, if I just make my payload equal this at this particular part, then I'll immediately hit this block of code and hit the vulnerability. So that's one disadvantage of fuzzing, is you might miss easy bugs like this, as opposed to if you were just looking at it in height approach. So like I said, when you're looking for bugs, use both approaches, use reverse engineering and use fuzzing. There's no reason to limit yourself. Actually, I want to draw one more thing up here, Bill, before you go away. So with generational fuzzing, just to give you a better idea of that, and you'll also see this with block-based fuzzers, which is like network protocol fuzzing, where you're sort of generating data instead of mutating existing data. They'll have you describe the specification. So for instance, let's say we're fuzzing PDF again. We would tell it first 3 bytes is the string PDF. We would be describing this like in some sort of template document. The next one is, the next 4 bytes is integer that's greater than 0 and less than or equal to OX 1000. Then I have an ASCII string here. That is null terminated and is less than 1024 bytes in length. Then I have another integer here that's unbounded. And I sort of specify this template document to the fuzzer, and it knows, okay, this is my specification. If I generate anything outside of this range, like if I generate a document with OX 10001, then the document reader just isn't even going to accept the document. It's going to say, this isn't a valid PDF document, so I'm just going to reject it. I'm not even going to try to render it and parse it. But it'll know these are all the quarter cases, so I'm going to generate a document where integer is 0, where it's OX 1000, where my string length is 0, where it's 1024 bytes long. And for the unbounded integer, it'll probably try things like 0, OX FFFFF, and all those other boundary cases. It's just going to try to exercise all these boundary cases in unison. Does that make sense to you guys? So a generational fuzzer like this, there's like a Peach fuzz is one that people use, and Sully is one that's used for like fuzzing network protocols, where you kind of do the same thing. But part of the problem with those fuzzers is generating those template files can be really annoying to go and like describe the full protocol in that sort of manner. But it is effective once you put the initial work in.
I'm assuming other people have already generated templates for widely used or...
I believe so, yeah, but I think a lot of those people, they kind of hold on to them and they're kind of close-held because they don't want to make it easy for other people to find bugs or whatever. So like yeah, so with Peach Fuzz, their business model is kind of, we'll give you this really good generational fuzzer, but the documentation is kind of spotty and it's really hard to use. So while the fuzzer is free, to actually use it, you have to take our 3-day training to actually learn how to generate the template files and all that and learn how to use it. Because with theirs, I believe you have to generate all this stuff in like crazy XML format. That's really kind of like, ghastly. But I guess once you do all that and learn how to do it, it's pretty effective. But I generally don't use that approach, just that's my personal preference. The only time I'll use generational fuzzing is when I'll use a block-based fuzzer like Spike or Sully, which will generate network protocol interactions based on a specification like that. But it's much easier to specify, a lot more friendly than kind of the crazy XML format that PHFuzz uses. Okay, and then another approach for finding bugs, just because I wanted to stick with my fishing theme, is noodling, where you like have your arms and you try to catch catfish with it. You know, they like put their arms under the rocks and let the catfish bite them. Totally awesome. I think only people in like the deep south do this. But the only thing I could think of representative of this is like reading the documentation. So you'd be surprised the type of bugs you could find just by reading developer documentation. For instance, in the program documentation, you'll often see like this particular feature of our application is buggy or is known not to work right, or this feature is legacy and it's old and no one really uses it. And when you read those things, you want to hone in like, okay, well they're saying this feature is buggy. That's definitely the type of code I want to exercise for trying to find bugs. Sometimes it'll even say, under these circumstances, our program will crash. It's like, oh, okay, well I definitely want to check that out. So you can find all kinds of good stuff just by reading the documentation for a program. Especially if there's like a developer forum or something like that for the program. You know, people will go and post like public bug reports or public problems with the program, and you can read those and say, okay, yeah. So it sounds like they're getting a crash, and just based on what they're describing, it could be like a buffer overflow, so I definitely want to check that out. And you know, for the developers, that's like number 100 in their queue, so they're not going to get to it for weeks, but you can hone in on it directly, develop an exploit, and then you have an exploit that is unpatched for the next month while the developers are getting around to it, developing the patch. Okay, do you guys have any questions about those general approaches I just described? All right, so the program we're going to be fuzzing is Corey's Crappy Document Reader, and these are some examples of what it can do. So it has this proprietary document format, the .cdf format, and it can render pictures, draw some text, like an arbitrary number of lines of text. It can have a title window, and that's really about it. So when we're wanting to fuzz Corey's Crappy Document Reader, we want to choose a document that exercises all of its features, right, for those reasons I was just describing. And that's easy in our case because Corey's Crappy Document Reader is very simple. So even just this document exercises all its features. It draws a background, draws multiple lines of text, has a window title, etc. All right, but here are the rules of the game. Corey's Crappy Software Company has a very aggressive legal team, and if you put your software into IDA Pro, they're going to sue your ass like crazy. So you're not allowed to do that, okay? So our only avenue for trying to find bugs is fuzzing. That's what we're going to do. Okay, so already talked about that. Before we go further, I'll let you guys just see what Corey's Crappy Document Reader is. So if you go into your class directory, I think there's like a CDF reader. Hang on, let me just get caught up with you guys here. Remember to turn dep off, guys. Okay, so yeah, we have this, where is it? CDF directory right here, and C:/class CDF. And then the CDF reader executable, and then you can use it by typing in the name in on the console and the path to the document you want to render, which is any of these CDF documents. So for instance, Fuji.cdf. Oops. What was that?
Wrong tab.
Yeah.
Wrong class.
Oh. Thank you. Obviously, Corey's crappy software company puts a lot of resources into error checking its arguments, which is good for us. So there's an example. You guys just all make sure you can get one of them to work. There's a few CDFs I put in there. Has everyone got the CDF reader displaying something at least? Okay. So I think the one we'll use is our fuzzing sample, but you are welcome to, you can look at those CDF files and choose which ones you want to fuzz. For our case, we're just going to be fuzzing one document. We'll load one document as our sample size, one that we know exercises all the features, since there are a limited number of features here, and puts bits in it at random locations. So you can choose whichever one you want, and you can even program your framework to use multiple ones of the files if you're good enough at Python. But for the simple framework I gave you, it's just going to use one known good file and fuzz based off that. So if we were fuzzing PDF reader or a PDF, Adobe PDF, we would want to basically make one document with like Adobe PDF generator that included every possible feature Adobe Reader had to offer. So remember, our general plan is here. We're going to take this known good file. We're going to mutate it a little bit just by like flipping random bits in the file. We're going to take that mutated file, try to get CDF Reader to render it, and then that's going to generate us a set of crashes. And then we're going to look at those crashes later on today and try to decide whether or not we think that those crashes represent exploitable conditions in the CDF Reader. All right, so let me show you guys the fuzzing framework so you guys can modify it if you want. So if you go to C:/class fuzzing, you'll see the cdffuzzer.py in here. And you can open it with whatever text editor you want. And there's a lot of stuff in here, a lot of which you should not change because the fuzzing framework depends on it. It's just a simple PyDebug script I wrote. What you should think about changing is this create fuzzy document function. So right now, if you understand Python at all, or really any type of program, it should be easy to see that what it's doing is it takes in a known good document, which is like a blob of binary data. It selects a random index into that file, which is this first part, random.random integer 0 length to original document -1. And it sets that random index equal to a random byte value. And it just returns that document back to the original calling function. And the calling function is going to take that mutated data and send it to CDF Reader. So a little bit about how this fuzzing framework was written. I use what's known as PyDebug, which is like a scriptable Python debugging interface for Windows. And it's like pretty much the best thing since sliced bread for finding bugs in Windows. You can just kind of like write your own little simple debugger that has lots of cool functionality with Python. So you can, right here, basically, the way this is working is, you scroll down to the main function, I'm registering an exception handler. Let's see which one it is. So I basically register this as the exception handler in the code, which is very easy to do. And this function just gets called whenever the program I'm debugging crashes or has an access violation, which is obviously the things we want to hone in on. And prints how many crashes I have, how many times I've tried to generate a crash. It stores a copy of the document that generated the crash, and it also writes to a file a general analysis of the crash. So PyDebug also has this really cool functionality for basically dumping out the state of all the registers when the crash occurred, what the state of the stack was, and all other kinds of program state information we can use to try to extrapolate whether or not we think the crash was exploitable. And you can see right here in the start process thread, this is where I'm actually registering the callback. And I'm just telling it, okay, PyDebug, I'm registering this as the debugger for this program that I'm about to launch, and any access violations, call this Python function for me. So PyDebug is really easy to use, and if you want to do this type of thing, I suggest you go and read the documentation some, and you're obviously free to take this framework and do whatever you want with it. So just looking at the main function a little bit more, we can see it's basically just looping forever. It opens a known good document. Or it's open the known good document up here, rather. Based on the known good document, it mutates the data a little bit. It writes the mutated data back to disk. It starts a thread that is going to run CDF reader on that mutated data. And this start process that is also going to register this script as the debugger for the process. It's going to let it try to render for like a second, and after a second, it's just got to kill the process. It assumes that if it hasn't crashed after the first second of execution, then it's never going to crash. And then it just keeps doing this over and over and over again. It keeps logging those crashes. So feel free to look around in that file, figure out how it works. But what I challenge you guys to do is look at this create fuzzy document function and modify it how you see fit. So right now I'm just flipping one bit in a totally random index in the file. You can modify this if you want, but please just modify this create fuzzy document one. And you can program it to modify more than one random bit at that location. You can make it modify not set something to a random byte, but maybe you think the OXFF byte is the one most likely to cause a crash, or the OX00 byte. You can make it change it so it's only modifying bytes in the first 1,000 bytes in the file or something like that. It's totally up to you. So I want you guys to take like 15 minutes and think about how you want to modify this. And to help your decision, I will let you put one of these CDF documents into HXD, just so you can get an idea of what it actually looks like. So you can look at the document in a hex editor, just try to get a feel for what all is in here, and try to use that to inform your decision. But take 10-15 minutes and modify this if you want to. Now, if you don't want to modify this, that's totally okay. This approach will work as well. But we'll have a little race and see who can generate the most crashes at the fastest rate. And this one probably will not win if someone comes up with a better solution, because there are better solutions than just doing it this way. Now, what you could do, I will say, is, if you modify too little data, you might not get a crash. But if you change too much data, that's not good either, because if you change too much data, the document reader might say, this isn't even a CDF document, so I'm not even going to try to parse it. So you kind of have to find like the sweet spot in between. So once you guys have made the modifications you want to, you're welcome to start the fuzzer. And to do that, you just go with the console to the C class fuzzing directory. And just do Python cdf fuzzer.py, and it'll start running. Now beware, though, when you restart the fuzzer, it's going to wipe out any previously saved results that you had. So it's got to create a file, crashlog.txt, and a directory crash docs. And it's going to put all the crash analysis in crashlog.txt and all the documents that generated crashes in crash docs. And whenever you restart the fuzzer, it's going to clear those things out. So if you want to save your results and like redo another fuzzing run, just make backups of those files and directories. Crashlog.txt and crashdocs. So once you've got that going, you're welcome to start your fuzzer.
Crash my fuzzer.
Guess one of your modifications to the fuzzer wasn't so good, huh? And if you're like a beast Python programmer, you're welcome to try to make this faster, like more, parallelized. Because obviously right now, you could be doing this a lot faster than just sort of one every half a second. For a while, guys. You'll want to get like 10 or 15 crashes probably, at least.
Just count if they all hit the same byte.
Maybe or maybe not, because the byte you may be causing a crash on may or may not be exploitable. So you probably want to expand that and at least get a diverse set of crashes. So one part of fuzzing that I was going to bring up later, but I'll go ahead and say now, is that the crashes you could generate like 3,000 crashes, but only a small set of those are going to be unique. So yeah, I can fuzz XPDF reader and get 3,000 crashes, but a lot of those are going to be crashing on the same EIP, on the same crash condition, so maybe only like 3 or 5% of those will be unique. So let's say I've got 100 unique crashes out of my 3,000 total crashes, and then only a small set of those are going to represent underlying exploitable conditions. So in general in fuzzing, you'll see a lot of repeat crashes, and one part of programming a fuzzing framework is being able to crash bin and like determine how many of the crashes you have are actually unique. So how do you think you guys would do that? What sort of rules would you use for determining whether or not a crash was unique or whether or not you've already seen it before? You don't have any ideas? Yeah.
Almost export the documents together and see the general vicinity that it's crashing.
Can you think of like a way that would be easier to do programmatically? So one sort of easy rule of thumb would just be to bin them by what EIP they crashed on. But that isn't necessarily the best thing, because if they got to that EIP via 2 different paths, if I have like an IDA diagram and it did like that and got a crash, and one that went like that and got a crash, this one may be exploitable and this one may not be exploitable. So the EIP would be the same, but they're really kind of like 2 different crashes because they took 2 different flows to the program. So yeah, like picking in the call stack, the stack status is one thing you can do. There's no really, right solution. You just want to think of what your heuristic would be for identifying which crashes are unique and which ones you've already seen before. Okay, so out of curiosity, who has more than 5 crashes? How many crashes do you have back there?
Roughly 20-some.
20?
77.
77?
Did you win? 6.
Who has the most crashes out of the VBcast people?
I've run it a few times and I think it's my count.
I'm just randomizing the first 2 of it's a file.
So, you that got 77 crashes, what was your strategy for your fuzzer?
I set some variable percentage to fuzz, and then I just fuzz that many random bytes.
Yeah. And are the bytes you're fuzzing, you're generating random data, or are they hard-coded bytes that
Yeah,
you're...
right now they're just random data.
Okay.
I was running through that while looking for other things.
So Zeno, if you wanted to write 4 bytes into the file, you could do something like
No, I mean like hard-coded 4 bytes. So without doing like 4 separate writes of 1 byte, when you do the actual fuzzy document and you're indexing into it, it doesn't like me to put 4 bytes as the right-hand side.
yeah, it's because that's considered like a byte array.
So how can I cast it?
You could use the you Python pros, I can do that with hack, right?
Yeah. It's less than 7.
So if you add this line, you know, import struct. And then come down here and make it fuzzy document, you know, index, whatever the index is. Struct dot, what is this? That one's hack, right? Then I, and then OX. That's right for you Python people. I'm just like a Python hacker. I really don't know that much about Python development. I just know that some things are easier to do in Python, so I go and kind of on the fly try to figure out how to do them. But you have to make sure, so you know that your index is less than the length of the file minus the number of bytes that you want to write. So if you did this right on, you know, the last byte of the file.
Zero's network died.
Okay.
There's no easy way to insert in the middle.
You would have to like, you know, just create 2 different byte arrays, and then the middle part, and then just concatenate them all together.
I got the EIP to be 1.
To be 1?
1.
Interesting. Think that's exploitable?
I don't know. It's touch.
All right, so I'm going to run mine with, I'm not going to change it to a random byte. I'm going to change it to, let's see, who thinks if we were just going to set 1 byte, you know, instead of making a random index random byte, we've set it equal to like a hard-coded byte, what would be the best byte to change something to generate crashes?
Which byte or what line?
Like the value that we're changing it to.
Looking for an overflow.
Yeah, so FF is a good one. And it actually kind of depends on what your target is. Like Windows heap stuff, there are certain bytes that represent like certain parts of heap structures that are good, like OXPD or something like that. But in general, OXFF is kind of like the best bet. Because it's going to, you know, potentially unsigned integer, signed integer, and make things really big and so forth.